So here's a weird question for you. Can a molecule have a right hand and a left hand? Just like we do? It sounds a little strange, I know, but it's a huge concept in chemistry. Today, we're going to dive in and unravel this whole puzzle by looking at one really cool molecule to see exactly how it works.
And this is the big question, right? How is it even possible for something that's built from the exact same atoms to exist in two different mirror image forms that you can't stack on top of each other? Well, the secret is all in its three-dimensional shape.
Okay, so to understand the whole thing, we've got to start with the individual pieces. Think of it like looking at the parts list in an IKEA box before you start trying to build the furniture.
And here it is, the star of our show today, ruthenium tris-ethylene-diamine, or for short, RuEN32+. Right in the middle, you've got a ruthenium metal ion, and then attached to it are three identical things called ethylene-diamine.
So what on earth is ethylene diamine, or EN as we'll call it? Well, in chemistry speak, it's a bidentate ligand. But honestly, the best way to picture it is like a tiny, flexible molecular clamp. It's got two teeth, in this case they're nitrogen atoms, and it uses them to grab onto that central metal atom in two places at once.
All right, we've got our parts. Now let's see how they all snap together. We're moving from the parts list to the assembly instructions, and you're about to see this really beautiful symmetric shape start to form.
The assembly process is actually pretty straightforward. First, you've got your central ruthenium atom just sitting there. Then, one by one, those three ethylene-diamine clamps come in and just lock on. And as they attach, they naturally push each other as far apart as possible, which forces the whole thing into this very specific, very stable 3D shape.
And what you end up with is this perfect shape called an octahedron. Each one of those little molecular clamps forms a super sturdy five-sided loop with the metal. We call that a chelate ring. And the result is this beautifully symmetrical, stable molecule. But if you look really close, there's a hidden twist in this perfect shape. And this is where our story gets really, really interesting. I mean, we've built this perfectly symmetrical object from identical parts. So where does this whole handedness thing even come from? Time for the big reveal.
This is the key question, isn't it? If I gave you a set of identical building blocks, you'd expect to build the exact same thing every single time. But in the molecular world, it turns out how you twist those blocks into place matters a lot.
And here's the answer. It's so cool. Those three ethylene-diamine clamps can wrap around the central metal in one of two ways. They can create a right-handed twist, kind of like a normal screw or a boat propeller. We call that one delta. Or they can create a left-handed twist. We call that one lambda.
And this is the kicker. As soon as that first clamp attaches with a certain twist, the other two are pretty much forced to follow its lead. It's an all-or-nothing situation. The entire molecule gets the exact same handedness. You can't mix a right-handed twist and a left-handed one in the same molecule.
And this brings us to the official scientific term. These two versions, the delta and the lambda, are what we call enantiomers. They are perfect mirror images of each other, but you can never, ever stack them perfectly on top of one another. It's just like your hands. They're mirror images, but try as you might, you can't superimpose your left hand perfectly onto your right.
Sometimes the best way to understand what something is to look at what it isn't. So to really get what makes our molecule so special, it helps to see the kinds of structures it actually can't form.
So check out this table. You can see right away that while optical isomerism, that's our handedness thing, is a big yes, another really common type, called geometric isomerism, is a definite no. It just can't happen here. But why not? Well, it's actually pretty simple. Geometric isomers, things like cis and trans, need different parts to arrange in different ways. Like this group is on top and that group is on the bottom. But in our molecule, all three of our clamps are identical. There are no different sides or groups to arrange. There's just one perfectly symmetrical way for them to fit. Okay, so we've looked at the parts, the assembly, and that really unique twist. Let's put it all together now. Think of it as a final, clear-as-day identification card for our molecule. So let's sum it all up. What's on this ID card? Well, its geometry is octahedral, we know that. Its electronic state is low spin, which is just a fancy way of saying its electrons are all settled in and super stable. Its symmetry is called D3, which is the specific mathy name for this elegant three-bladed propeller shape. And finally, its possible isomers. It's not just one thing, it's two mirror image forms, our right and left-handed enantiomers. And there you have it. That's it. We've just figured out the complete stereochemical identity of this molecule. That's the full 3D picture.
Not just what it's made of, but its exact shape, its electronic properties, and of course, its incredible, unique handedness.
So this leaves us with a final thought to chew on. We just spent all this time on one single molecule, but this whole idea of handedness, what chemists call chirality, it is literally everywhere. It's absolutely crucial in medicine, in the flavor of our food, even in the DNA that makes you, you. It really makes you wonder, doesn't it? Where else is this invisible, fundamental twist quietly shaping the entire world around us?